Hi, welcome to this FMSP online revision recording. This one's for Edexcel FP3, and we're going to be taking a look at further coordinate systems, which means the objects, the ellipse and the hyperbola. These are both called examples of conic sections. You need to know various things about them, such as their Cartesian and parametric equations. You need to know how they're defined in terms of a focus and a directrix, and that involves a number called the eccentricity. You're doing standard things with them, working out tangents, normals, and solving loci problems. So we'll see some examples of this in this session. If we take the example of the ellipse, so the standard Cartesian form for an ellipse is x squared over a squared plus y squared over b squared equals 1, and you can see if you substitute x equals 0 and y equals 0 into that, you can see that these points are on this ellipse. So there's a0 on the x-axis and minus a0, and 0b and 0 minus b on the y-axis. So the ellipse is kind of a squashed or stretched circle horizontally and vertically, and this one will look something like that in terms of a and b. Here's the x-axis and here's the y-axis. The focus and the directrix is another way to think about how the ellipse is defined. In the case of, and they're associated with a number called the eccentricity. So in the case of the ellipse, the eccentricity is a number between 0 and 1 called e. And if you think about that, that means the point AE0 will be here, and then A over E will be here. Now AE0 is called a focus, and the line x equals A over E is called the corresponding directrix. So this is x equals a divided by e, and those two objects have this property in relation to the ellipse. If you take a point on the ellipse, you take its distance to the directrix and multiply it by the eccentricity. That will be its distance to the focus, and that defines the points on the ellipse. Likewise, there's a negative x-coordinate focus here and a vertical line through a negative x-coordinate, which is x equals minus a over e, and the points here have the same property in relation to those 2 points. One other thing that you need to know, well, there's a couple more things. First is there's a parametric form for an ellipse, which is x equals a cos t, y equals b sin t. So as t varies from 0 round to 2 pi, you pick up all the points on the ellipse, and then finally the relationship between b, a and e for an ellipse. So this can be expressed as b squared equals a squared times 1 minus e squared. And there are similar things and similar properties in relation to a hyperbola, and we'll see that in the question that we look at about hyperbola. Okay, so here's our first question. We have the line x equals a is the directrix of the ellipse, who's got the standard equation with a and b greater than 0 here, and 2, 0 is the corresponding focus. Okay, so if we let e be the eccentricity for this ellipse, then we know that a times e will be equal to 2, that's the x-coordinate of this focus, and a over e will be equal to 8, that's the value of x, the x-coordinate that the points on this line take. So we have two equations involving a and e. We can multiply them together so that we get ae times a over e, which gives a squared on the left hand side, equals 16. And from this we can deduce that a is 4. A can't be minus 4 because there's a convention here that a is greater than 0. And that gives us the value of a. And we also have to find the value of b, and we can use this relationship between b, a and e, which is b squared equals a squared 1 minus e squared. So we have a value for a, so that means we'll need a value for e in order to work out a value for b, and of course we can use either equation 1 or equation 2. So equation 1, for example, says ae equals 2. We now know that a is 4, so this is 4e equals 2, so this is telling us that e is actually a half. And so now if we go and use this, we get b squared equals a squared 4 squared times 1 minus a half squared, which is 16 times 3/4, which is 12. And so b is the positive square root of 12, which will be 2 times the square root of 3. There's 5 marks for that. Let's have a look at the mark scheme for this. So yeah, you can see here that we're using a over e equals a and a times e equals 2. So we're needing to know those standard facts about the eccentricity, the focus and directrix, and how they relate to the Cartesian equation, the a value in that. So there's a couple of marks for knowing that and forming those equations, for using them together to get a value for A. Then there's using this relationship between B, A and E correctly to work out a value of 2 root 3 for B, and that's worth 5 marks in total. The other question we're going to look at is about a hyperbola, and as a reminder about this, the standard equation of a hyperbola is x squared over a squared minus y squared over b squared equals 1. And again, the point A0 is on this hyperbola, and if you take well, the thing about hyperbola is that it also has an eccentricity, but this time it will be a value bigger than 1, which means that AE, which is a focus, is further out from the origin than A, and A over E is closer towards the origin in terms of that particular point. So here's a directrix, x equals A over E, and here's a corresponding focus. And again, the points on the hyperbola, whoops, I didn't mean to come around quite like that. The points on the hyperbola have the property that if you take the distance that they are from the directrix and multiply it by E, that will be the distance back to the focus there. Some other things you need to know, again, there's a relationship between B, A and E, so B squared is this time A squared times E squared minus 1. Notice the opposite order for the subtraction there compared to the ellipse. And parameterized forms again, well, we have a couple of forms for this. So we have x equals a sec t and y equals b tan t is one option, or x equals a cosh t and y equals b sin t is another possibility there. Okay, so let's have a look at this particular question. I'll just draw some sort of picture of this. So we have, of course, in this one we've got a equals 4, so it'll pass through this point here, 4, 0. I'll try and make a better job of drawing it this time. Okay, so we've got a point P on our hyperbola, and you see it's kind of given in terms of this parameterization, a sec t, b tan t. So it corresponds to a particular value of t, and we're being asked to think about a tangent called L1. And so we've got to use calculus to show that the equation of that tangent is given by this, first of all. Okay, so there are various ways you can do this. You could differentiate the parameterization and use the chain rule to get a value for dy by dx. I'm going to differentiate this expression here, so taking the standard Cartesian form of this hyperbola, I'm just going to differentiate the left hand side with respect to x and the right hand side with respect to x. So that will give me x over 8 minus y over 2 and then times dy by dx, because that's the chain rule and the implicit differentiation there, equals 0. So this gives me that y over 2 times dy by dx is equal to x over 8, which tells me that dy by dx is equal to x over 4y. So at our point P, which is where I'm taking the tangent, I need to sub in the value of the x and the y coordinate to this. So we're going to get the x coordinate is 4 sec t, the y coordinate is 2 tan t, so that will give me 8 tan t there. I'm just going to write this more simply. So the 4 over 8 I'll write as a half, sec I'll just write as 1 over cos t, and tan I'll write as sine over cos, but it's inverted there, so it's cos t divided by sine t, just making everything nice and simple in terms of cos and sine. These cancel, so I end up with 1 over 2 sine t. So that's the gradient then. What I'll do now is I'll just use the standard form for an equation of a line through a point with a certain gradient. So I'm just using here y minus y1 equals m x minus x1 to get the equation of L1. So that will give me y minus 2 tan t equals 1 over 2 sine t and x minus 4 sec t. I'll just make myself a little bit of space over here to finish that off. So I'm just moving up into that space there. The next thing I'm going to do is multiply through by 2 sine t, so that will give me 2y sine t minus 2 tan t times 2 sine t equals x minus 4 sec t. And I can see this is getting close to this kind of equation, so I'm going to leave the 2y sine t there, I'm going to leave the x over there, and I'm going to add on the 4 tan t sine t, and then we've got minus 4 sec t. So this looks quite close to what we need. I just need to work on those n2 terms. So common factor of 4. Tan t is sine over cos, so we've actually got sine squared t over cos t minus 1 over cos t. So we have 2y sine t equals x plus 4, and then I've got sine squared t minus 1 over cos t. Now sine squared t minus 1 is minus cos squared, so imagine that the numerator is minus cos squared, and you'll see that we get x minus 4 cosine t, which is what we need. Okay, so we've now got an equation for L1, and we'll move on to the next part of the question. So I think, once again, just for clarity here, I'll draw this diagram again. So we have our hyperbola, which passes through 4, 0, and of course there's a corresponding arm on the other side of the x-axis, of the y-axis here. We've got our point P with its tangent L1, whose equation we've just worked out. So now we've got another line L2 which passes through the origin and is perpendicular to L1. So I'll try to add that to my diagram here. So that will be a right angle, and this is L2. We're told they intersect at Q, and it says show that as t varies, the equation of the locus of Q is this thing here. So as t varies, P will move around, L1 will change, and therefore L2 will change, and Q will change as a result of that. So how are we going to attempt to work out that this is the locus of Q, or show that it's the locus of Q? So first of all, I think we need to work out Q perhaps in terms of t, get an x and a y coordinate for it in terms of t. So what do we know about Q? Well, it's on the line L1, which we know is 2y sine t equals x minus 4 cos t. It's also on the line L2. Now L2 is a line through the origin, so L2 is just of the form y equals mx. Now m is the gradient. Now if you remember, the gradient of the line L1 was 1 over 2 sine t. So that means the gradient of L2 will be the negative reciprocal of that. So that will just be minus 2 sine t. So I'll just put the x there just so it kind of looks okay. So that's just y equals mx with m being minus 2 sine t. So we've got two equations now, one for L1 and one for L2. Let's call them 1 and 2. What I'm going to do is I'm just going to substitute this for this, so the value of y in terms of x from L2 into L1 to give us an equation just involving x and t. So that will be minus 4 x sine squared t equals x minus 4 cosine t. And I'm just going to make x the subject of that, so that will give me 4 cos t equals x times 1 plus 4 sine squared t, and that means that x is equal to 4 cos t divided by 1 plus 4 sine squared t, and y is just a matter of multiplying x by minus 2 sine t, so that will be minus 8 sine t cos t over 1 plus 4 sine squared t. Okay, now I've now got x and y in terms of this parameter t, but I need to show this is a Cartesian equation for that locus as t varies. So what I'm going to do is I'm just going to work out what the left hand side is, this expression here is in terms of t, and then I'm going to work out what the right hand side, this expression here, is in terms of t, and hopefully we'll see the same expression, which means that the equation we were given there is the locus of Q. Okay, so what I'll do is I'll just write these two values out again first of all. So x we worked out in terms of t was 4 cos t divided by 1 plus 4 sine squared t, and y was minus 8 sine t cos t over 1 plus 4 sine squared t. Okay, so we'll start with the left hand side then, which is x squared plus y squared squared. So I need to square this, which is 16 cos squared t over 1 plus 4 sine squared t squared. I need to square this. That's going to be 64 sine squared t cos squared t, again over 1 plus 4 sine squared t squared, and then it's also the square of that. Okay, so I can pull out 16 cos squared t over 1 plus 4 sine squared t as a common factor in this square bracket term. So let's do that. So we've got 16 cos squared t over 1 plus 4 sine squared t squared is the common factor inside this square bracket. So we need 1 plus, and then it will actually be 4 sine squared t here. And then of course we're squaring that as well. So notice that this 1 plus 4 sine squared t here will cancel with one of them in the denominator there, and then we're squaring what's left, so that's going to be 256 cos to the 4 t over 1 plus 4 sine squared t all squared. So that's the left hand side in terms of t. Let's move into this space here now and have a look at the right hand side. So this is 16x squared minus 4y squared. So that will be, well, we need to square this again. That's going to be 16 and times 16. So that will be 256 cos squared t over 1 plus 4 sine squared t all squared minus, and then 4 of the square of this. So if we square this we get 64, and then 4 of that will be 256, so, and it'll be sine squared t cos squared t over 1 plus 4 sine squared t squared. Okay, so again we've got lots of common factors here. We've got the whole of the first term, in fact 256 cos squared t over 1 plus 4 sine squared t squared times 1 minus sine squared t. And of course 1 minus sine squared is sine squared t is cos squared t. So again we end up with 256 cos to the 4t over 1 plus 4 sine squared t all squared. And we note that these expressions are the same. So in terms of t they evaluate to the same, so they are the same. So we have a proof that this holds for all the points on this locus Q, and that is the equation of the locus of Q. Let's have a look at how the marks work out. Notice that there's an alternative version here to get the gradient of the first tangent as 1 over 2 sine t, using the chain rule and differentiating the parameterization with respect to t. And of course it all drops out in the same way. So there's some method marks for getting the gradient, using the standard method for getting the equation of a straight line, and some accuracy marks for 5 there. There's a method mark for and an accuracy mark for getting the equation of the line perpendicular to that through the origin, so using the fact that you get the negative reciprocal as the gradient, and then intersecting those two lines, getting values for x and y, 4 marks for that, and then showing that we have the correct parameterization. There's a couple of marks there for this algebra and the use of these identities at the end to show that they're the same. I hope that was useful. If you want to know more about the Further Maths Support Programme, please visit our website, or if you want to look at more revision videos, please visit our website. Thank you very much.